Let us move on to the next one, that is electronic effect. We will be mainly focusing on the inductive effect. In the later part, we will be studying about resonance, electromeric and hyperconjugation. So, when we study about acid strength, how do we explain the following trend? If you look at the various acids are given here, substituted acids, acetic acid, iodoacetic acid, bromoacetic acid, chloroacetic acid and fluoroacetic acid. If you look at the pKa, in other words the acidity of these various acids, when we talk about acidity, we are talking about the acidity of this particular carboxylic acid proton. So, in the first case in the acetic acid, it is less acidic, that is 4.8. Whereas, when we talk about fluoroacetic acid, it is 2.59. In other words, fluoroacetic acid is a very strong acid compared to acetic acid. So, how do we explain this trend? Acetic acid is less acidic compared to fluoroacetic acid, which is very high acidic. Do we have any method by which we can actually look at the molecule and predict it is going to be more acidic or less acidic? So, this is one of the questions that is being answered by our inductive effect. So, what is inductive effect? When we say induction is basically the redistribution of electron density through a traditional sigma bonded structure according to the electronegativity of the atoms involved. So, here again the electronegativity plays a vital role in deciding how the electrons are distributed between the bonded atoms, and we will be looking at why it is important at the later part of this course. So, here is a definition for inductive effect from the IUPAC Gold book. An experimentally observable effect on rates of the reaction etc. of the transmission of charge through a chain of atoms by electrostatic induction. So, this is what is called inductive effect. Do not worry about the definition, we will be looking at the effect and then you will understand much easier what does this mean. As it is mentioned, inductive effects are generally considered to be transmitted through the sigma framework of a molecule. So, what is the sigma framework of a molecule? Let us look at an analogy here, then we will try to understand how it actually works. So, this is a molecule given here. X is basically, let us assume this is a halogen which is more electronegative than carbon. So, when we talk about inductive effect, it actually works through the sigma bonded framework. So, how does it actually work? So, you can see a pictorial representation or a cartoon here. So, this is a halogen. In the tug of war, this halogen is actually pulling these people towards itself. So, that is how the electrons which are present here in the sigma framework are being pulled by the highly electronegative halogen atom. So, this is what is a pictorial representation for you to visualize how an inductive effect works, and this happens through the sigma bond. So, in other words, what we can say is the electrons, the sigma bonded electrons are pulled towards the halogen more, and what we can say is the inductive effect and the field effects are basically influenced in the same direction by the structural changes in the molecule. So, in other words, wherever the electronegative atoms are there, they will pull the electron towards itself through the sigma bonds. That is what is called inductive effect. And as we have mentioned, induction is the redistribution of electron density through a traditional sigma bond. So, let us look at an example here. So, this is a lithium, methyl lithium. So, in this particular compound, what we have is lithium's electronegativity is 0.98, whereas the carbon's electronegativity is 2.5. So, between these two things, which is more electronegative? You know, carbon is more electronegative. So, what we have mentioned here is it is basically the carbon. So, the carbon is more electronegative than the lithium. So, that means you can very well say that the electrons will be pulled towards this particular carbon because this is more electronegative. It is not necessary that always the heteroatom will be the most electronegative one. We have to look at the electronegativity, then we have to decide what element is going to be more electronegative. So, here lithium is 0.98, so this is less electronegative, that is, in other words, we say this is electropositive compared to carbon. So, this is the electron density distribution map. So, here you can see this is blue in color. When it is blue in color, that is said to be electron poor, and when it is red in color, that is said to be electron rich. So, that is how we can say in this particular molecule the carbon is having more electron density compared to lithium, and this happens because of the induction. And if we take another example, here we have a carbon. So, this is nothing but the chloroform.
Methyl chloride.
So, the electronegativity of these two elements, chlorine is 3.16 compared to carbon, which is 2.55. So, now you know exactly which is more electronegative. The chlorine is more electronegative. So, this will pull the electron towards itself as shown here. So, when we look at the electron distribution map, so here you can see there is a huge red color. In other words, what we can say is this is a place with more electron density or electron rich, and there is a blue color at the bottom which is having, as we have seen in the previous case also, this is electron poor. So, that means the carbon which is having low electronegativity is pushing the electron towards the chlorine, which actually pulls the electron towards itself. So, this is basically the redistribution of electron density that is based on the electronegativity difference of the atoms that are involved. So, we can actually see a pictorial representation of how the inductive effect works. So, we will move on to the next one. Here what we look at is basically about inductivity effect in aromatic systems. So, if an atom or a group withdraw electrons away from the carbon, then it is called minus I effect moiety, and if it pushes electron towards the carbon, it is called plus I effect moiety. So, like the previous one, let us take, we have a carbon and a lithium, we have carbon and halogen. So, now which is going to be a plus I effect group and which is going to be a minus I effect group, you can actually identify. In the case of carbon and lithium, this is 0.98, this is 2.55. So, this will be actually pulling the electron towards itself. In other words, the lithium will be pushing the electron towards here. So, that means this is going to be a positive I effect group. And in the case of carbon and halogen, this is close to, this is 2.5 and this is 3.2. So, this will be actually pulling the electron towards itself. In other words, this is going to be minus I effect group. So, that way, with respect to carbon, we say a group is either plus I effect group or minus I effect group. So, this is with respect to carbon we are talking, because in organic chemistry we deal with carbon mainly. So, that is the reason whenever we say an inductive effect group, that means either it pulls the electron towards itself or it pushes electron towards itself. Based on that, we say whether it is a minus I effect group or plus I effect group. If it pulls, then minus. If it push, then it is plus. So, this is how you have to remember. And in the case of aromatic systems, based on hydrogen, a group is said to be plus I or minus I. So, there is a difference between normal alkyl carbons and aromatic system. Here we have some examples of the plus and minus I effect groups. Alkyl groups push electron towards carbon. So, this is what is called, it is a plus I effect group. As we have seen, halogens actually are more electronegative than carbon. So, they pull the electron towards itself. Oxygen and nitrogen also pull the electron towards itself because of more electronegative than carbon. These groups are called minus I effect groups. For the same atom attached to the carbon, depending on its bond order and the charge, there is a change in the effect. For example, if we take the hydroxyl ion, this hydroxyl ion is attached through oxygen. We have an oxide which is also attached through oxygen to a carbon. So, between these two things, can we decide which is going to be plus I effect and minus I effect? Actually, that depends on the bond order and the charge. In the case of hydroxyl, this is actually pulling electron towards itself because oxygen is more electronegative. So, hydroxyl group is minus I effect, but oxide group basically has additional negative charge here. So, due to which this is actually electron rich, even though oxygen is electronegative, this is having more number of electrons. So, basically this oxide gives or donates electron to the carbon, that is why this is called a plus I effect. So, you cannot simply say oxygen is always minus I effect because it is electron withdrawing. No, you have to look at the bond order as well as you have to look at the charge also. Based on that, you will say how the particular group is, whether a plus I effect group or a minus I effect group. And also the bonding position also plays a vital role. Whenever the substituent is on the alpha position, the inductive effect is found to be maximum. When it moves away from that alpha position, that is beta or gamma position, the inductive effect reduces. Here we look at some more groups related to plus I and minus I effect. The order is given in the decreasing order for donation or withdrawal. So, O minus group followed by Cr3, CHR2, CH2R and methyl group. So, this is methyl group is having the least donation compared to O minus group. So, these are the electron donating plus I effect groups, and when we talk about electron withdrawal, that is minus I effect, NR3 has the highest withdrawal ability compared to OH group. So, how the electron is actually pulled or pushed through the sigma framework is given with an example. As here you can see the NO2 group is basically electron withdrawing, that is minus I effect. So, it pulls the electron towards itself, and the methyl group is a plus I effect. In other words, it actually pushes the electron. So, that means if we consider the central carbon, one group that is present here, the nitro group, pulls the electron towards itself through the sigma bond framework, and the methyl group actually pushes the electron towards the central carbon again through the sigma bond framework. So, these are called the plus I effect for the methyl group and the minus I effect group for the nitro. And let us look at the application of inductive effect. The plus I effect actually confers stability to carbocation. So, the more number of methyl groups, as we have seen, this is a plus I effect group. Carbocation is actually an electron deficient species. So, this is requiring electron, and this group can donate electron. So, we know the methyl group is a plus I effect group, otherwise it will actually push the electron. So, when it pushes electron, this actually stabilizes the carbocation, because carbocation is having a positive charge. In other words, this is electron deficient. When there are two methyl groups, what happens? Both the methyl groups actually push electron towards the carbocation. That means the stability actually increases, because the carbon now gets more electron from the methyl groups. And when we move on to the tertiary butyl group, what happens is there are three methyl groups, and all the methyl groups actually donate electron to the electron deficient carbon. So, the stability of the tertiary carbocation becomes very high compared to methyl. In the case of methyl, hydrogen does not push the electron, because this plus I effect is very less. So, in other words, the hydrogen cannot stabilize the electron deficient carbocation. So, the methyl cation is very unstable. There is also another application here. We will see in the beginning of our inductive effect, we have actually compared the acidity of acetic acid with various halogen substituted acetic acids. Here we are looking at acetic acid and methyl substituted acetic acid. So, in this particular case, we have one methyl group substituted. We know methyl group is a plus I effect group. There is one plus I effect group. There are two plus I effect groups, and here we have three plus I effect groups. If you look at the acidity, acetic acid is more acidic. See here, the lower pKa means stronger acid. So, here it is having 4.78, which is a low number. That means this is more acidic compared to pivalic acid, which is less acidic, because this pKa is 4.93. So, why this difference happens? Actually, in this particular case, we want to generate a O minus and a H plus ion. So, when the H plus ion is left, we end up with a negative charge on this particular oxygen. This is already electron rich. If more electrons are being pushed towards this particular carbon, that means that actually increases destabilization. So, that is the reason when three methyl groups are pushing electron towards this particular carbon, and when the acid is formed, that is proton is lost, we have a negative charge here. So, more electron is flowing towards the electron rich center, in other words that leads to destabilization. So, this destabilization is responsible for lesser acidity of pivalic acid compared to acetic acid. So, this can be explained based on the inductive effect. So, these are some of the applications of inductive effect. We can also have other examples. As we have seen, the inductive effect basically drops across every sigma bond, involving limiting its efficiency to a few bonds. That is what we have seen. Whenever it is on the alpha carbon, it is having the maximum, and whenever it goes to beta or gamma position, the inductive effect reduces. So, this is what we have seen earlier. So, here is an example which we can actually compare for that value. So, this particular methylene carbons, it has 2 protons. In the case of NMR signals, this bromo derivative, the NMR values are coming at 3.3 for the alpha carbon,
hydrogen,
and it goes to 1.69 for the beta and 1.25 for the gamma position. So, in other words, the electronegativity pulling of the bromine diminishes or decreases when we move away from that particular atom. So, this is how here it is experiencing the maximum electron pull from the electronegative halogen. This carbon experiences less pull and this carbon experiences much less pull, due to which the NMR values are actually changing here. So, the upfield shift of this proton is due to the less inductive effect experienced by this particular methylene group by the bromine. And the inductive effect also can be used for explaining the decreased acidity between formic acid and acetic acid. In the case of formic acid, we have a proton hydrogen. In the case of acetic acid, we have a methyl group. That means this actually pushes more electron towards this particular carboxylate anion. So, that is less stable compared to formic acid, which does not actually push any electron towards this particular carboxylate anion. So, that is the reason the formic acid is more acidic compared to acetic acid. And here some other examples are given for methanol, ethanol, isopropanol and tertiary butanol. So, if you look at the pKa values, you see methanol is having the least value of 15.5. So, this is more acidic compared to tertiary butyl alcohol, because this pKa is very high. In other words, this is much less acidic compared to methanol. And similarly, the position, when we talk about the distance from the carboxylate unit, if it moves from this is the alpha position, then this is a beta or the 2 position, and this is gamma or the 3 position. So, we have a comparison of pKa for 3 different acids. So, this difference in the acidity can also be explained using the inductive effect. So, chloroacetic acid is 2-chlorobutanoic acid is having very high acidity compared to 4-chlorobutanoic acid. So, this can be explained using inductive effect, that is the position of the halogen which is present at 1, 2 or 3 position. And similarly, the minus I effect increases the acidity. So, here again this example we have already seen in the beginning, and the application of inductive effect can also be used for the electrochemical properties of various metals. So, here in this particular case, the concept of inductive effect between the phosphate ion is actually replaced by the sulfate ion in a polyionic cathode material to increase the electrochemical property. So, this is again based on the inductive effect. So, these are some of the varied applications of inductive effect. And in the case of drug development also, inductive effect plays a vital role. So, this particular amide having pKa 5.8 is having a higher binding affinity to carbonic anhydrase compared to the methane sulfonamide. We have a CF3 group, that is a trifluoromethyl group, having higher binding affinity compared to methyl group. So, this is having a lower binding affinity. So, this 5-fold binding affinity increase or the acidity is due to the inductive effect. So, this plays a vital role in the drug development also.